Again, this lecture covered exponential functions, which is chapter 5, section 1 of our course textbook. Our main objective is to learn how to graph exponential functions and also how to evaluate exponential functions. So if we have equation y equal to 2 to the power x, this is an example of exponential function because x is an exponent. So exponential function is if we have a and the value of a is greater than 0 and it's not 1, then the function f at x equal to a to the power x is an exponential function. Again, here the condition is a can be any value, but not a negative value, which means you have to be greater than 0 and also not 1. So the first example here, we are going to graph y equal to 10 to the power x. This is an exponential function. Now to graph any function, first thing we need to do is to set up our table. We should know the values of x and y. So here we can set any interval, and we decided to set an interval of x between -3 to +3. So again, when x is -3, y will be 10 to the power -3, which is 1/1000 or 0.001. Then when s is -2, y will be 10 to the power -2, which is 1/100. When x is -1, y will be 1/10. And when s is 0, y will be 1. 10 to the power 0 is 1. And all the way to 3. Now we can graph the points we have. So when s is -3, y is almost 0.001. Then when it's -2, it's 0.01. When s is -1, then we have 0.1. When s is 0, y is 1. When s is 1, y will be 10. So this will be, the exponential function. So exponential functions of the form f at x is equal to c times a to the power x. Here the c value have to be greater than 0, and also the a value must be greater than 1. And this is called exponential growth function. So in an exponential growth function, in our case of c, it can be any value greater than 0, which is positive value. And also a will be any value greater than 1. So the exponential growth function, the graph will be in this form, because as s increase, y will be increasing exponentially. So the function y equal to f at x, which equal to c times a to the power x, where c is greater than 0 and also a is greater than 1. And we may have what we call the exponential growth function. Now here we have an example, a bacterial growth. A single bacterium split into 2 bacteria every half hour. So the number of bacteria in a culture quadruples every hour. Thus, the equation by which a colony of 10 bacteria multiplies in t hours is given by the following. So y equal to 10 times 4 to the power t. So this will be, again, an exponential growth function. The c value is greater than 0, and also a is greater than 1. So the question here says we should graph equation for the time t between 0 to 8. So this means our interval will be from 0 to 8. Now when t is 0, we can see from here that we are going to get 10. Because 4 to the power 0 is 1, 1 times 10 is 10. And when t is 1, it will be 40. When t is 2, 4 to the power 2 will be 16 times 10, so 160. So again, here we are going to have exponential growth, and this will be our function after we get enough points. Next example is we have $10,000 that is invested at 6% and is compounded monthly. Then the future value of the investment is S after X years is given by the following formula. And we can see this formula also again is an exponential function. 10,000 times 1.005 to the power 12x. Now the question says we should find the future value of the investment after 5 years and also after 30 years. So first, we are going to substitute x with 5 since it's 5 years. So we get 10,000 times 1.005 times 12 times 5. And this will give us 10,000 times 1.005 to the power 60. 12 times 5 will give us 60. And after using our calculator, we get 13,488.50. Now in B, the time is 30. So we substitute x with 30 and we use our calculator. And our solution will be 60,225.75. Now we should note that the amount after 30 years is significantly more than the amount after 5 years, a result consistent with exponential growth models. So as again the t increases, the x will increase exponentially. We also have a special function that occurs frequently in economics and also biology, which is e to the power x. E is a constant value, which is 2.71828. Now, because e should be greater than 1, the graph of y equal to e to the power s will have the same basic shape as a growth exponent, since e is 2.718. So we have a growth exponential function. So we can again calculate the y coordinate for points on the growth of this function with a calculator. Most calculators have e to the power x key. So here our question says we should graph the function y equal to e to the power x. So again, we may choose any interval for x. Here we chose -2 to +2. So when s is -2, y will be e to the power -2. When we use our calculator, we will get 0.14. Now, e to the power -1 will be 0.37. E to the power 0, again, anything raised to the power 0 is 1. Then e to the power 1 will be 2 decimal places, will be 2.75. Then e raised to the power 2 will give us 7.39. So we can use the 5 points here. When s is -2, y is 0.14. When s is -1, y is 0.37. So we draw our 5 points and we get the shape of our graph, which is a growth exponential function. As s increase, y increase exponentially. We also have the exponential decay function, which means when s increase, y would decrease. And this would be in the form of y equal to a to the power -x. So when s increase, y will decrease because a to the power -x is the same as writing 1 over a to the power x. So we can see that when s increase, the denominator value will increase and that will decrease the y. So here we said that the same condition, a must be greater than 1. And also we have another form, y equal to c a to the power -x. As far as c is greater than 0 and a is greater than 1, we still have, again, exponential decay functions. So the condition here said if y equal to f at x and is equal to c times a to the power -x, if c is greater than 0 and a is greater than 1, then we have exponential decay function because the exponent is -x. So it will be a reciprocal 1 over a to the power x. So when s increasing, getting bigger, the y value will decrease. Or sometimes we may have a positive x, but here we have c times b to the power positive x. But in this case, c also should be greater than 0, but b must be between 0 to less than 1. It must be greater than 0. So b cannot be a positive value and it cannot be a 0 value. It have to be greater than 0, but it cannot be greater than 1. You have to be less than 1. If it's greater than 1, then we are going to have a growth function, exponential growth function, if b is greater than 1. So b should be greater than 0, but less than 1. If the x exponent is positive, we still have decay function. So here we can examine the similarities and also the differences between the graphs of y equal to f at x, which is equal to a to the power x, and also those of y equal to m times f at x, or y equal to f times kx, or y equal to f at x plus h, or y equal to f at s plus c for constants of m, k, h, and c. We may see this example again in section 5.3. So here, if we have y equal to e to the power x, it will be exponential growth function. But if we multiply by a negative value, it will be almost like a symmetric of the function. But we can see that when we multiply by a positive value, it will grow more exponentially because it's going to double. So if I will have y equal to e to the power x, then y equal to 2 times e to the power s will again double to be more. As s increase, y will grow more exponentially, bigger value than y equal to e to the power x. So here we say from the graphs, we can see that if m is greater than 0, the shape of the graph is still that of a growth function, but more rapidly increasing. Then when m is less than 0, as we saw it, the shape of the growth exponential function will be upside down, or will reflected through the x-axis, making the range y is less than 0. So in all cases, the asymptote is unchanged and is the negative x-axis. In each case, the y-intercept will be 0 and then the m value. So that will be the conclusion of section 5-1. In this section, again, we learn the basic concept of exponential function and also how to graph it. Now in section 5.3, we are going to again solve exponential function or equation problems. Thank you for your time.